So the thing I'm going to talk about today is no-instrumentation Golang logging with eBPF. There's a lot of like words in there, but we'll go unpack this over the next few slides and some demos. But before we get into that, let's quickly do a background about myself. So once again, I'm Zain Asgar. I'm the co-founder and CEO of Pixie Labs, which has actually been acquired by New Relic. So now I'm the general manager of the Pixie team at New Relic. And as part of this acquisition, we're actually going to be open sourcing pretty much everything inside of Pixie and then continuing to work on it as part of New Relic and building a new open observability system. In addition to that, I'm also an adjunct professor of computer science at Stanford, working mostly on like machine learning and then systems research. Prior to this, quick background, I used to work in Google's AI team, working on like machine learning at scale. And then I've been at Stanford and NVIDIA, working on graduate school and also working all the way from chip design to eventually machine learning at NVIDIA. Cool. So with that, let's kind of get started about what developer problem we're looking at, and and what we're looking to solve over here. So I'm sure many of you have actually dealt with this in production programs, right? Where you're an application developer, your application isn't working as expected. So typically, the first thing you do is go look at logs, and you're like, what's going on? Like, why is something not working correctly? One of the problems that a lot of times you realize is that like the log is actually not in the spot that you need it. And typically you go on some like debug loop, either guessing as what's going on, try to find some other logs that will hopefully help you. At some point, you might actually get desperate enough that you actually go add new logs and then redeploy the application and then find out what's going on. So typically, this is a pretty long process, right? Depending on what companies you work at, it could be like a few hours to get a new deploy, or it could even be like a few days or weeks if you're in a company that doesn't deploy very often. Another option that people typically look at is using a debugger, right? And debuggers can be attached to production code, even though it's like pretty sketchy and can be rife with a whole set of problems. But without further ado, we'll quickly walk through what a debugger looks like and how it works. And I'm sure most of you are familiar with this, but I'm just going to review the basics just to set the baseline. So with Go, people typically use Delve. You can also use GDG and other debuggers, but Delve has like pretty good support for the Go runtime and data structures, and it's extremely easy to get started, right? You just go get Delve and then you run it, and we'll look at that in 1 second. But before we do that, I wanted to point everyone to this demo application we'll be playing around with today inside this talk. It's purposely kept really simple and trivial, but the idea is that we'll be able to demonstrate most of the things we're talking about. The code's located at this link over here, but believe me when I say that it's basically an HTTP wrapper around this function. So it exposes one HTTP endpoint called /e, and then you pass in a number of iterations. And what will happen is the HTTP handler will basically invoke this function called compute e with a number of iterations. And this just does like an iterative approximation of the natural number e, right? So it just runs through this loop for the fast number of iterations and returns the approximation of e. It's not a very complicated program, but it'll demonstrate most of the things we'll talk about. So let's say that we go back to our original problem. You're like, my compute e function is misbehaving. How would I figure out what the number of iterations that is getting called in with? Like maybe there's some bug somewhere in the logic which is changing the number of iterations. So what you would do is you would go stick in like a printf over here, and then you would figure out, or a log statement or something, and then you would figure out the number of iterations. Now, if you don't want to actually go modify your binary, you can do the same thing using a debugger, right? So what I did over here is just ran delve exec the app, and then I set a breakpoint on line number 15, and then which happens to be where this function is located. And then I just started the server. When we hit the endpoint, as soon as it hits that point of the code, it'll stop executing, and I can print the iterations and print the value inside of the for loop. So so far it's pretty simple usage of a debugger. One of the nice things about debuggers is that they also provide you all the context. So if I do backtrace, you'll actually see what the call chain for this function was. And like I said earlier, compute E is basically called by some HTTP handler, which is this anonymous, function, which is ultimately called by the serve HTTP function. So it's not much there, but just to be fully out there, it is a very, very simple piece of code. We can also get a visibility into the Go runtime. Just to do a quick recap over here, debuggers provide us an easy way to get information about executing code. There's like no need to add, printfs and recompile and do all the stuff. Keep in mind that running it on production code might be a little sketchy because it actually stops executing your code. So you might actually break things because of timeouts and other things that were there. Plus, you might not even be able to get access to it. Delve and GDB can connect a remote binary, so you don't have to log into the machine hosting the binary. There is support for remote debugging, and there's some pretty cool tools out there like Solo that allow you to actually run debuggers in Kubernetes environments. So it's pretty, there's some pretty nice scaffolding because this stuff has been around for a while. So actually, I put the next thing out there. Can debuggers be run on production code? Sure, you can do a remote attachment to production binaries. Unfortunately, they do actually mutate the binary and stop execution of the code and can lead to unexpected failures. Most people probably not brave enough to run these on prod. So what are your options, right? So you're back to the same old options. You can either add a lock to your program, recompile and redeploy, or you can be like, well, this bug is annoying. I really need to get it fixed. I'm gonna, bite the bullet and just try it out. There's some other Linux tracing utilities that work similarly, but the title of the talk has something to do with eBPF, so we'll talk about how to use eBPF to get the same kind of data. I'm going to stop over here for a second in case there are any questions. Okay, and like I said, feel free to interrupt at any point. So with that in mind, let's talk a little bit about what is eBPF. So eBPF is the Enhanced Berkeley Packet Filter. At this point, I would say it has far outgrown its name. Originally eBPF was designed as a system to build firewalls, and it was like a way to basically make programmatic firewall rules that run inside of the kernel. Nowadays, because of all the work that's gone into it by a bunch of different people, it's kind of turned into this sandboxed virtual machine that runs inside of the Linux kernel. So what happens with eBPF is that you typically take some restricted code or some verifiable code, which is usually a restricted C code that gets converted to this eBPF bytecode. And you can then insert this eBPF bytecode into the Linux kernel. And you do this as a system call in Linux kernel, so it doesn't require any new kernel modules or anything. So as long as you have a new enough version of the Linux kernel, you can send it the eBPF bytecode. The kernel will analyze the eBPF bytecode and make sure you're not going to do anything bad to the kernel, right? And then let you execute that code. And ultimately, what eBPF lets you do is do things like access system calls. You can even set these things called UPROs, which allow you to probe applications, which is actually what we'll be looking at in a few seconds. You can trace all the network requests and actually probe into a bunch of different kernel data structures in a safe way. Any thoughts or questions on this? Cool. Okay, so over the next, just as a preview, or the next few things, we're going to look at this feature called uprobes and eBPF, which is a user space probe. And we'll look at how to use GoBPF to actually build something that'll trace the code in the prior example. So what are we actually going to build? So we have our application here that's serving the HTTP binary, right? So that's this thing over here. We are going to write something called a uprobe function, which is a user space probe that'll capture some data from this application and write it to a buffer, right? And then we're going to build a second binary called a tracer, right, which is going to read this buffer and print it out. So at the end of the day, we will get something that basically takes the value from the application and prints it out over here in a completely separate binary. So in other words, it's very much like a debugger, except you get some of the benefits of eBPF, which is You can go safely modify this application to go insert the probe. It doesn't actually stop the application from running, so we'll capture the value and then it'll continue executing. And depending on where you put it, the performance overhead is usually quite insignificant. Cool. So diving into the details, how does this actually work, and what are we going to do? So all binaries, unless they've been stripped of all their symbols, will usually contain the actual symbols at some point, which is how when you get a stack trace in Go, it tells you what the name of all the functions are. So you can use this program called obj dump to take a look at the symbols. So that's what we did over here. And then we notice that this address 660980 is the main.compute function. You don't need to memorize this address, but just remember that there is an address where this function is located. And then we can see that the data is being moved from the stack pointer to the AX register. And this is the first argument of the function. So with that in mind, what are we going to do? So we have the application binary here. If you remember, the 660980 is where main.compute is located. If you dig further, you'll see that main.main is located at this address, 6609F0. What we're going to do over here is at this address, we're actually going to insert something called a uprobe hook. And what happens is that when the CPU hits this address, it'll actually, instead of executing the instruction at that point, it'll go ahead and execute your BPF program after trapping into the Linux kernel. So it does something called a soft interrupt. It doesn't do like a full context switch, but it'll trap into the Linux kernel. The Linux kernel says, oh, I know I need to run the BPF program. It'll run the BPF program, which at this point is just regular machine code because the kernel has deemed it to be safe. And we will use that and then write the data to the perf buffer. And then at some point later, the tracer binary will go ahead and read the perf buffer and get the values out. Cool. Okay. So this all sounds relatively complicated, but it turns out that code for this stuff is actually not too complicated. It's relatively simple. Here is the actual BPF program. There's some scaffolding to set it up, and it's also in this GitHub link below. But here's the key part of the program. So the first thing we do is, as I said earlier, most BPF programs are written in this restricted C format. So this is pretty much C code, but there's some rules around how to write it in order for the kernel to verify that the code is safe. So with that in mind, we include the ptrace stuff from the kernel, and then we say create a perf buffer called trace, and then we have this function called compute called, which, as I guess the name suggests, it gets called whenever compute is called. And then it gives you this thing called ptregs, which is the pointer to the registers. So you can basically think about it as when the context switch happens, it'll basically store all the register values in the pointer to the regs. So we know that the input argument is stored in AX, which happens from the first copy we saw. But you can also just go reference the Go ABI and know that this is where the input argument will show up, or you can look at it as an offset from the stack pointer. Either way, it works. So we read the input argument, and then we do a perf submit, which basically just writes the value to the buffer. And that's it. So this program is relatively simple. It gets registered in using uprobes, and it'll attach to every version of the binary that is running. The code in its entirety is located over here, but this is the main, BPF specific part. Everything else is in pure Go. So without further ado, I can dive into a demo. But before I do, are there any questions or anything you want me to dig into? Cool. Okay. So what I'm going to do over here is I'm going to quickly show you the app file. So there's this thing called app.go. And as I said, there's compute over here. It's the same code that you saw on the slides. And let me know if this isn't big enough. I tried to make this big-ish to read. And then the next thing over here is that there's an HTTP handler that says on /e, every time there's a get function, basically read the iters and then write compute iters to the output. So pretty straightforward. And then it just starts up the HTTP server. Okay, So I took the liberty to start up the app earlier, so it's serving the app on port 9090. So just to go through a demonstration of this, if I were to run this program, it provides me with a value of E. I ran it for 1,000 iterations, so I get a good approximation of E. If I curl this and run it for 1 iteration, it claims the value of E as 2. Not quite a good approximation of E. If I run it for, I don't know, some more iterations, like 3 iterations, I'll claim the value as 2.5. Just still not very good, but much closer to 2.7. So this is basically how this application works. So with that, let's take a look at the actual tracer. So there's this function called trace.go. And as I promised, here's the BPF program. It is exactly the same code that you saw on the slides. It doesn't highlight very well over here because this is C code embedded as a string inside of this Go program. Because ultimately what we do is we use this library called BCC, which will actually run Clang on the C code, convert it to BPF bytecode, and then ship it off to the kernel. So like I said, we don't use BPF directly because it's a little annoying to deal with everything. But ultimately, we create a new BPF module, we load a new uprobe, and then we attach a uprobe for our program. And then we create this table called trace. And then what we do over here is basically do a loop. We read the value from the channel, which is the trace channel. And then we note that we're running on an Intel CPU, so it's a little endian. So we read the 64-bit value and then just print it out. Well, do you have a question? You were on mute, I think. Nope. Okay. So that's what this thing does. So what I'm going to do now is I will start up this example over here. So as I said, trace example trace, and I give it the path to the binary. And then it does need to run as root because it's inserting stuff into the kernel. So now you'll see that when I run curl on it, it'll actually print out the values over here. So basically we get, whatever values we specify will get printed out on this side because we're tracing the application running on this window. And if you actually leave off iters, you'll see the default iterations is actually 100. Cool. Oh, sorry, I'm trying to find my, get back here. Sorry about that. Okay, just trying to find the right screen. Okay, so utilizing trace points for dynamic logging, gets us to a point where we can easily instrument binaries, and you can do this on production binaries, so it doesn't actually stop executing your code. You can just safely capture the values and then bail out. The thing I want to point out is the complexities of all the Go ABI and everything actually make this quite difficult to do. Like even for the simple example, there's a lot of reverse engineering. But if you think about, how interfaces and channels and all that stuff work, it's actually a fair amount of effort to get this to be done. Regardless, it's actually possible to build pretty complex set of applications. So some of you might have seen this pop up on my history on my shell. But another demo I was going to do is do an HTTP tracer. So this is actually built using a slightly different way. It's built using kernel probes. But I have a blog post on this. You can go and read the details of this. But I'll run the tracer for HTTP, and we specify the PID. And this is the PID of this process up here. So now when I curl this, you'll actually get the entire HTTP request, right? So it says status code 200, length 11. This is the content type, and here's the body value. So it's possible to build relatively complex systems by just using eBPF. And if I pass in some bad value emitters, you'll see that E is only 2. So this is just parsing the HTTP level stuff now in this application. Presumably, I can point this at any HTTP application. It actually isn't dependent on on this particular app. So it's a little bit more generic. Cool. With that in mind, that's kind of, I just wanted to showcase like what is possible. We've been, really influenced by things like Inspector Gadget by Ken Volk and stuff on Sysdig. And as I mentioned, I work at Pixie and now the New Relic Pixie team. And we're going to be open sourcing all this stuff. So one of the things that Pixie does is it actually allows you to programmatically write all these loggings and stuff into the Go programs, and also do analysis without modifying any code. And we're going to be open sourcing all of this stuff. So it actually makes using this information a lot easier and programmatic. So you don't have to write tons of like C code to access simple information. Yeah, that's all I had. I'm happy to take questions.
Thank you. I think there is one question asking about the ability to read memory is there for Go app. Can you write it?
So I believe eBPF actually has functions to go and modify memory. We, like at Pixie, we don't use it because we don't really want to modify the application because we don't want to accidentally break it. But it is possible in eBPF to go and modify memory. So I know that was a lot over there, but hopefully it was somewhat interesting. And if you're interested in the details, there are a couple of blog posts on our website that you can check out that go into a lot more detail. And obviously, like as we open source everything, like we'd love it if people follow along and give us feedback.
There is one more question, if there's time for you.
So it shouldn't really require anything special, and Pixie itself, which will be open source soon, is built for Kubernetes. So everything we do runs inside Kubernetes, and part of what we let you do is be like trace every version of this application across all different pods, right? Or things like that, and you can specify filters and get more information. So we actually support that natively in Pixie. There's nothing special. Last thing I'll point out is that while Pixie isn't completely open source yet, we actually have some stuff out on GitHub, and we have a community meeting every Thursday. We're going to be open sourcing everything over the next 2 to 3 months, but there is a version that you can try out for free completely. So we'd be happy if you try it out and give us feedback.
Thank you very much, Zain.